Okay, we're back on. Everybody, you guys are moving farther back. How can you hear me? Oh, I got you. Yeah, now I got you. I never think about stuff like that, and I should. Yeah, it's all right. Ugh.
How are you today?
I'm doing all right, but if for you guys who occasionally watch the news, one of the real uh, founders of modern rock and roll died, David Crosby. He was 81 years old, and I'm surprised he lasted that long. He had a liver transplant in '96. Phil Collins paid for it, but absolutely tremendous. I'll give you the same spiel. If you guys get MGM Plus, which used to be called Epics, which has got some good shows on it, one we particularly like, but there's one called Laurel Canyon. It's a two-part series that's done retrospectively with photographs of very, very famous people who in the rock and roll who were at that, and we're talking about the Mamas and Papas, the Byrds, Crosby, Stills, Nash, Joni Mitchell, and more. The Beach Boys hung out with them when everybody never associated the two musics, but Brian Wilson is one of the true musical geniuses of our time, and it wrote a very nice thing. And I'm amazed he survived this long. I mean, he lived in his room for 3 years. He wouldn't leave. He was so messed up. If you get a chance, and if you want, even if you put yourself on there and just disconnect it to watch that two-part series, or know somebody who has it, it's because they have the two people who did the photographs talk about the photographs of these people, and occasionally would interview somebody more modern, because most of them are going away. I mean, to me, Joni Mitchell is one of the all-time greats. So there's the song that really first came to their attention when I was in college. The album came out. They appeared at Woodstock in '69. It was the first time they appeared with Neil Young. It was called "Sweet Judy Blue Eyes," which is a tribute to Judy Collins, who Steve Stills was in love with. But she only became famous because she sang a song called "Clouds," which was by Joni Mitchell, who's one of the all-time great writers. And they've modernized a lot of her songs, so you would get a chance to listen to that. So much for any question of how I am, that was very impactful. You still there?
Yeah.
Okay, just wondering.
We're looking at charts.
Go ahead. Chart away. Moving on. So we begin. So I'm recording and I'm doing this. Okay, back to neuromuscular junction. Hopefully the sound comes through, or if I have to adjust it, we shall see. So this is really where we left off. We're looking, we first went through this slide with all of these events at the neuromuscular junction. And we'll look at the animation and probably get to more than one today that I feel are very, very good. And take a look at the events that go on. So to summarize, the impulse, which you control, sets up its own action potential, though we're going to look more closely at that, as it sends that signal. When the signal disrupts the membrane, eventually it opens a voltage-gated channel because effectively it's a voltage-gated current at the distal aspect of the motor neuron. And in doing so, it allows extracellular, and I make the distinction all the time between extra and intracellular, because it's important not to forget it. Extracellular calcium enters the motor neuron. That's what facilitates the exocytosis. That facilitates the V snares and the T snares. Acetylcholine is released, the neurotransmitter, into the synaptic cleft. It's such a small space with such a massive amount of molecules. It almost instantaneously, but that's the delay. That's the gap period, the latency period. That's so important that we're going to see down the road. And we see that in a lot of systems, the gap between the nervous signal and the actual electrical and mechanical events that come after it. So I think that's an important thing to note. So it happens, and it happens more quickly with voltage-gated channels than any other types of channels, particularly voltage-gated ion channels, which To my recollection, they all are. Sodium enters, potassium exits, 3-to-2 relationship, and it creates what we call an end plate potential, which in and of itself, one isolated gate is certainly not sufficient to create a true action potential, and you're going to see it has to achieve threshold. So the distinction in this unit between an end plate potential and the development of an action potential in the muscle fiber is significant and noteworthy. So the action potential arrives. They're showing the calcium entering the area. Now, next, you can see the exocytosis of the acetylcholine. Here you can see these are ligand-gated channels. Up here is a voltage-gated channel. The ligand in question is the acetylcholine. The acetylcholine attaches, and it facilitates the sodium in and the potassium out. Okay. So they're showing action potential, voltage-gated calcium. Calcium creates the exocytosis. Now the acetylcholine diffuses through at this area, the synaptic cleft, and of course the increased in surface area by way of the junctional folds. Here you can see the sodium in and the potassium out. It's not like there's one separate one, they're just the way they represent it. And then where we ended last time, the ways to terminate the signal. If not, you have a muscle that contracted and it could never relax. So it's going to stay contracted. And if you look at the fine print, the breakdown of the synaptic cleft of the acetylcholine and the termination of the effects is mostly due to the action of an enzyme that's always there called acetylcholinesterase. We have other acetylcholinesterases in the brain. We have something in our system called pseudocholinesterases, and there's a rare genetic problem with them that I'll have to look up and see. It impacts people undergoing anesthesia, but they typically don't. I don't recall it off the top of my head. But the acetylcholinesterases are the primary means. Some of the acetylcholine will diffuse. These are the three ways that any neurotransmitter disappears. Diffusion just goes away. Enzymatic breakdown, they can call it metabolism or breakdown, all the same thing. You're breaking, in this case, you're breaking it down to component parts. Acetic acid is all over the place. It diffuses away. And the choline, and this undergoes reuptake, has mechanisms to suck it back up into the nerve and basically retrograde it back, as you will see down the road, and for the nerve to reprocess it into yet more acetylcholine. They'll say acetylcholine. I think they're accenting the wrong syllable. It's like capillary, aluminium, our British friends. Look at that. I'll adjust the sound as needed.
Nerve impulses, also known as action potentials, travel from the brain or spinal cord to trigger the contraction of skeletal muscles. An action potential propagates down a motor neuron to a skeletal muscle fiber. The site where a motor neuron excites a skeletal muscle fiber is called the neuromuscular junction. This junction is a chemical synapse consisting of the points of contact between the axon terminals of a motor neuron and the motor end plate of a skeletal muscle fiber. The events at the neuromuscular junction occur in 7 coordinated steps. Step 1. An action potential travels the length of the axon of a motor neuron to an axon terminal. Step 2. Voltage-gated calcium channels open and calcium ions diffuse into the terminal. Step 3. Calcium entry causes synaptic vesicles to release acetylcholine via exocytosis. Step 4. Acetylcholine diffuses across the synaptic cleft and binds to acetylcholine receptors, which contain ligand-gated cation channels. Step 5. These ligand-gated cation channels open. Step 6. Sodium ions, shown here in red, enter the muscle fiber, and potassium ions, shown here in blue, exit the muscle fiber. The greater inward flux of sodium ions relative to the outward flux of potassium ions causes the membrane potential to become less negative. Step 7. Once the membrane potential reaches a threshold value, an action potential propagates along the sarcolemma. Neurotransmission to a muscle fiber ceases when acetylcholine is removed from the synaptic cleft. This removal occurs in two ways. 1. Acetylcholine diffuses away from the synapse. 2. Acetylcholine is broken down by the enzyme acetylcholinesterase to acetic acid and choline. Choline is then transported into the axon terminal for the resynthesis of acetylcholine.
Yeah, that should about do it. Okay, so that's really, and those animations in the series that you will see here are very good, and we have other good ones for the nervous system when we get to that. So, I mean, other things are occurring there. Obviously, you know, the nerve, we're going to have to reset all of those things with sodium, potassium pumps, and particularly between the nervous system and the muscular system, that's where the vast majority of our ATP goes to, as you already are aware. So a lot of things interfere with this event. So this is an interesting little nugget that's more clinical. This is an autoimmune disease because the acetylcholine receptors are being broken down by antibodies. We'll explore it a little bit here in AP2. What are you doing in immunology now? I'm just curious. Okay, innate versus adaptive. Okay, so you're, and we do a quick review about that type of thing. I mean, to me, it's like, that's like military boundaries. This is the way I do it. I'm a little, as you know, a little mashuk. That's Yiddish for crazy. So myasthenia gravis is this disease, and what happens is the muscles that you use frequently tire most rapidly. So the early signs, we move our eyelids constantly. They droop, swallowing, generalized muscle weakness. I've had more than one patient with this over the years. It's not that terribly uncommon. There's more advanced ways to treat it now. Okay, so myasthenia gravis, and they fatigue very easily. This is not the equivalent of something like chronic fatigue syndrome. There's different things that are involved. They look more at that, at the sodium potassium pumps and malfunctions in that as being one of the areas that's explored for this. But myasthenia gravis is a bit more specific. So the sarcolemma, and this is just back to that cell animation. The sarcolemma itself, like any other membrane, is polarized. Inside the cell, right along under the membrane, negative compared to the outside. So the action potential is able to cause those changes first by a limited change. That is the end plate potential. That's a short signal with regard to how far it goes, and it really dissipates relatively quickly. The distinction is when it is sufficient to reach threshold, it will extend and trigger a series of gates that are voltage gated sensors, first sodium, then potassium, and that will lead, and that's the distinction. So the concepts, and again, the terminology here is very specific to neuromuscular junction and muscles. Depolarization and repolarization. Depolarization means it's going away from its polarized state, it's becoming more positive. Repolarization is a reset that you will see. So the acetylcholine binds to the acetylcholine receptors on the sarcolemma, chemically gated, ligand gated channels, sodium in, potassium out. So the sodium diffuses in, more positive, localized. So again, we start always, it has to be localized. I mean, when you decide to move something, you've gone past those steps, obviously. The end plate potential is generated at that junction, and they're showing you it creates a limited wave. The question is it going to get over to here where the next series of voltage gated channels are that are part of the muscle fiber? So generation and propagation of an action potential. If the end plate potential causes enough change in the voltage to reach what we call threshold. So typically it's around minus 70 millivolts. Threshold is about minus 55 ballpark. You know, that's an acceptable number. That's even the way I phrase questions. It's usually or approximately. So it's not good. I'm not going to give the answers are 55, 53, 52, and 57. Maybe I'll do that. Yeah, that's not the finger you were going to use. It's okay. A very gladiator of you. Thumbs up and thumbs down. Thumbs down was a bad thing if you're a gladiator. Sort of like Queen of Hearts. Off with his head. Love that. Large influx of sodium. What happens is once it triggers that channel, you get a mass of sodium coming in that's unstoppable. And at that point, that's what threshold means. Once you get there, it's going through the whole muscle fiber. The action potential spreads in all directions. That's another important distinction between that and a nerve. Very important distinction. Okay. Across the sarcolemma from one voltage gated channel to the next, causing a sequence we call depolarization. So it reaches there. How does it? Now what happens is it's generated and it's propagated, because what you're doing is you're rapidly changing the resting membrane potential sufficiently to go to the next set and to the next set in every direction. So sodium enters, the electrical chemical gradient, it follows, the action potential spreads adjacently, opens more voltage gated channels, and again, ripples in water, whatever analogy works for you. Immediately after that, the channels that are adjacent but down from or farther away from the initiation point are potassium voltage gated channels. So it immediately starts to correct itself by allowing potassium to undergo efflux following the concentration gradient. The potassium efflux out of the cell rapidly brings the cell back to its initial resting membrane potential. At that point, you have a slew of sodium in and a slew of potassium out. That's when those sodium-potassium, ATP channels, those sodium-potassium pumps, become active to restore the chemical basis. So it's a constancy. There is a refractory period, and you'll see this in the animation. It's all about that, what's called the inactivation gate. Sodium channels have it, potassium channels don't. The muscle fiber cannot be stimulated for a specific amount of time. In nerves and skeletal muscle, it's very, very short. Its effect, I would hate to use the term negligible, but let's say effectively, it's negligible, barring some other co-medical circumstance, some irregularity, chemical or otherwise, in the person's system. Not so in the heart. Very significant. That's what causes in the heart, when we get to cardiac function, the very famous absolute refractory periods. What you have in nerve and muscle are absolute, very, very small, where it can't be restimulated, and relatively refractory periods where an additional stimulus will cause it to recontract. But it's not that extended quarter of a second absolute refractory period as we have in the heart. So the muscle fiber can't be stimulated until repolarization is complete. Just can't. Okay. The ionic conditions are restored by the pumps. Yeah, sodium out, potassium in, blah, 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 blah. Here we go. So this is what you're seeing. The channels open, you get a typical spike. And we're going to see a lot of spikes when we get to electrocardiograms. But effectively, we're seeing a spike for depolarization as it rapidly goes about the size of more than a millivolt. Here you can see effectively minus 90 to plus 30, but it's around a millivolt, and then back down again. Okay. So what happens is sodium channels close and potassium channel opens. And what happens is we start to get close to back to the resting membrane potential, you're going to see that inactivation gate swings away. The sodium channel is still closed, but taken off the lock. The deadbolt's gone. I'm trying to be clever. As they say, TC by H, BH, too clever by half. Excitation, contraction, coupling is what we're talking about here. That's the next major phase. The excitation, once we get past the synapse and the neuromuscular junction and we activate those downstream voltage gated channels, now, well, how are we going to get them to go from electrical excitation to mechanical? So the events that transmit along that action potential, along the sarcolemma rather, excitation are coupled eventually to sliding those filaments. It's how does this occur? Now we're going to look at the events that occur along the T tubules where additional voltage gated channels are located. So that signal isn't done with sodium and potassium. As it enters within the framework of that muscle fiber, we contact voltage gated calcium channels that are within the fiber, and the calcium is intracellular, stored there, and is able to release it at the passing of that signal into the sarcoplasmic reticulum. And again, electrical events precede mechanical events. So it's that sequence that we'll see here, and they're going to summarize it. Here's the neuromuscular junction. Now, here's that potential reaching the start of these T tubules that surround all of these fibrils. Invest them. Okay, so it's really extensions of the sarcolemma that surround the individual fibrils and carry the signal deep within. As it's carried in, it contacts these voltage sensitive proteins that are sort of associated with both the T tubule and the terminal cisternae, with one on either side, creating the triad. Can't read that. Okay. And once that intracellular calcium floods the area, now it's going to attach itself to the troponin plugs. Anything that attaches to a protein changes its shape. So it alters the shape of that protein. The tropomyosin now no longer being fixed to that location slides away, exposing the active sites to each other, and we get the phenomena of contraction. Voila. The myosin cross bridge develops and it contracts. You'll see it here.
Typically, a single motor neuron arising in the brain or spinal cord conducts action potentials that travel to hundreds of skeletal muscle fibers within a muscle. The sequence of events that converts action potentials in a muscle fiber to a contraction is known as excitation-contraction coupling. If we look at a single muscle fiber, we see that an action potential travels across the entire sarcolemma and is rapidly conducted into the interior of the muscle fiber by structures called transverse tubules. Transverse, or T tubules, are regularly spaced enfoldings of the sarcolemma that branch extensively throughout the muscle fiber. At numerous junctions, the T tubules make contact with the calcium-storing membranous network known as a sarcoplasmic reticulum, or SR. Where it abuts the T tubule, the SR forms sac-like bulges called terminal cisternae. One portion of a T tubule plus two adjacent terminal cisternae is known as a triad. The membranes of the T tubule and terminal cisternae are linked by a series of proteins that control calcium release. As an action potential travels down the T tubule, it causes a voltage-sensitive protein to change shape. This shape change opens a calcium release channel in the SR, allowing calcium ions to flood the sarcoplasm. This rapid influx of calcium triggers a contraction of the skeletal muscle fiber. Thus, calcium ions are responsible for the coupling of excitation to the contraction of skeletal muscle fibers.
What I like best about that, as I pointed out, is it shows you the extent, so more or less you can get sort of a three-dimensional appreciation of how it surrounds. And it's typically, you're going to see most of these seem to be placed around that A and I band junction area for the most part. Seems to be where they seem to follow that pattern on a microscopic basis. So what they're saying, when the intercellular calcium is low, meaning it's in the storage wells, it's in the cisterns, okay, the tropomyosin blocks those active sites. It's holding the troponin is holding it in place. Myosin heads cannot attach to the actin, the fiber is relaxed. And those voltage-sensitive proteins, when they change shape, they release the calcium. So when it's released, it becomes high intracellular, binding to troponin. Troponin changes its shape, the tropomyosin, then it's released to move away and expose what are called myosin binding sites, again, named for where they attach, to on the actin filaments. Myosin heads then bind, cross bridge, and cycle. And then eventually the sarcomere shortens because of this. When nervous stimulation ends, calcium is pumped back into the sarcoplasmic reticulum and contraction ends. And again, the energy expenditure, you have to expend energy to send a signal from the brain to the spinal cord and the spinal cord out to whatever muscle it's going to target. That energy, you're going to expend additional energy for those sodium potassium pumps to function to reset the system rapidly for the next one. Then you're going to have to spend energy to pump the calcium back in when the signal dissipates. And as you will see, you have to spend yet more energy to detach and reset, because those heads are good to go. They are reset. They're ready to go. So 4 steps of, now the next and last step of this is basically the cross-bridge cycle. The cross-bridge cycle, they classically describe it in these 4 events. We get into the detail a little bit more than we do with the A and P1 students when I teach them that, like I did last semester, where they basically, okay, cause it to contract and release. Here you have to know a little bit more about what the ATP does when it hydrolyzes. So that is, so there's a touch more detail, and that's really what it is. Cross-bridge formation, the high energy, why are they high energy heads? Because they were preloaded or pre-cocked. They attach to the actin thin filament at those 2 sites that are so close to each other. That generates the power stroke or pivoting and pulls the thin filaments. And that's really all that's happening. The thin filaments, which are attached to the sarcomeric boundaries at the Z discs, are pulled closer together. Closer together. It's a whole line from an Abbott and Costello movie. I know, a long time ago in a galaxy far away. Did you ever hear the comedy routine, Who's on First? No. Bring back radio. Cross-bridge detachment. Now, in order for it to detach so it can fire again, the ATP attaches to the myosin head, causing it to detach, recocking it. And then as it hydrolyzes from ATP to ADP, okay, effectively, the attachment of the ATP releases it. The hydrolysis of the ATP permits to go back into the high energy state for the next cycle. So imagine you're lifting something heavy, out of the car, and you're bringing it into the house, a couple of packages, So they summarize these. And again, they're hard for me to read. Here you have the formation of the cross bridge. By that point, the cross bridge has ADP and an inorganic phosphate. When it does the power stroke, they are released. Now, in order to release the head, ATP has to bond, and then to reset the head, it has to hydrolyze. That's what I was referring to. To them, to the other, to the first year nursing students, by and large, it's like the ATP attaches, boom, good to go. For you guys, a little bit different. So you have to see that the ADP and the inorganic phosphate are there, but once the power stroke occurs, they're released. The ATP has to rebond, yes, again, to release the head from the actin, and then has to hydrolyze in order to reset it for the next go round. Here's the animation. And you're going to see the offsets.
The contraction of a skeletal
how
muscle
it does so
generates the force
continuously.
necessary to move the skeleton. A contraction is triggered by a series of molecular events known as the cross-bridge cycle. In a skeletal muscle fiber, the functional unit of contraction is called the sarcomere. A sarcomere shortens when myosin heads in thick myofilaments form cross bridges with actin molecules in thin myofilaments. The formation of a cross bridge is initiated when calcium ions, released from the sarcoplasmic reticulum, bind to troponin. This binding causes troponin to change shape. Tropomyosin moves away from the myosin-binding sites on actin, allowing the myosin head to bind actin and form a cross bridge. Also note that the myosin head must be activated before a cross-bridge cycle can begin. This occurs when ATP binds to the myosin head and is hydrolyzed to ADP and inorganic phosphate. The energy liberated from the hydrolysis of ATP activates the myosin head, forcing it into the cocked position. A cross-bridge cycle may be divided into 4 steps. Step 1, cross-bridge formation. The activated myosin head binds to actin, forming a cross bridge. Inorganic phosphate is released, and the bond between myosin and actin becomes stronger. Step 2, the power stroke. ADP is released, and the activated myosin head pivots, sliding the thin myofilament toward the center of the sarcomere. Step 3, cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and actin weakens, and the myosin head detaches. Step 4, reactivation of the myosin head. ATP is hydrolyzed to ADP and inorganic phosphate. The energy released during hydrolysis reactivates the myosin head, returning it to the cocked position.
That's really
as long as the binding sites on actin remain exposed,
and there's
the
calcium.
cross-bridge cycle will repeat.
That's how it really shortens expensive.
And as the cycle repeats, the thin myofilaments are pulled toward each other and the sarcomere shortens. This shortening causes the whole muscle to contract. Cross-bridge cycling ends when calcium ions are actively transported back into the sarcoplasmic reticulum. Troponin returns to its original shape, allowing tropomyosin to glide over and cover the myosin binding site on actin.
The only little nugget that's in there that I don't think is the distinction that when the cross bridge that you have to have, that you need to recall that first the inorganic phosphate strengthens it, and then the ATP leaving causes the actual power stroke. To me, just think of them as simultaneously rather than there's a certain amount. That for you guys, MCAT and graduate, that's the distinction. You start looking at those things even in more detail. I mean, that's kind of how it works. It's all detail oriented. And then when someone researches it and looks at it, it's way above my pay grade. My middle one says makes my head hurt thinking about that. It's even my oldest, despite all the important things he does, he never set foot in a science classroom in his collegiate career. Go figure. Nevertheless, okay, I love this because I am all into those kinds of and students really got into this stuff in the early days of CSI and those shows. Now there's 48,000 of them. Okay, and that's the concept of what rigor mortis is: death, rigidity upon death, and it's explained here that, and it depends on atmospheric conditions, and it depends on the body, and it depends on a variety of other factors, but more or less. So a forensic scientist would basically look at the ambient temperature, they check the body temperature, and they'd have a formula that they could easily determine, they know it off the top of their head, as to how long that theoretically, assuming the body wasn't kept in the freezer or refrigerator, like we do if you're going into a medical school program where you're doing cadaveric dissections, you keep them on ice. I mean, we have refrigerated chambers. See all those things. So 3 to 4 hours death, approximately normal circumstances, muscles begin to stiffen with peak rigidity, and you learn the difference between initial and peak by touch. Intracellular calcium levels increase because ATP is no longer being synthesized, so the calcium cannot be pumped back. So what happens is those voltage-gated channels go first and flood the area with calcium. And so the muscle doesn't know whether it's been a neurological signal or just more calcium in there because somebody died. So, the troponin changes, the tropomyosin changes, the muscles contract. And since there's an abundance of calcium, they reach a certain peak of rigidity. Then over time, they deteriorate. Now the proteins begin to denature. Okay, but ATP is needed for cross-bridge detachment, so they stay bound, constant state, but they stay contracted until the muscle proteins denature or break down, causing myosin to release. So that's why there's a lot of things forensically that are important. When somebody dies, you stop digesting. So stomach contents, certain things, like vegetables. If you had a salad, that stuff stays in there for a while, and you can check how long it is. The other thing is position. How do I know if a body is moved? It's called liver morsis or lividity patterns. When your circulation stops as soon as somebody dies. Okay, so if they're lying, if they're in bed, the blood should start to pool, assuming they're sleeping on their back. You should begin to see somebody would look at it after they died in a funeral home, let's say, and you see the blood pooling on their back. If they're on their stomach, you see it on their stomach. If you find them on their back and the pooling is on their stomach, somebody moved them. Now maybe they moved them to do CPR, okay, but then you'd have to have an explanation of why they were moved. Those are the things. It's fascinating. And as I said, it was started again, relatively within the last 30 years, everybody became attuned to it because of a very, very prominent trial of arguably the most prominent visible athlete of his time was O.J. Simpson. Good. Michael Jordan, O.J. Simpson, a few years after Tiger Woods, the two would go. And because of that murder case, when they first really started to see DNA and forensic evidence, we learned a lot about them. Whatever your feelings are about the case, but that notwithstanding. I think he's guilty, but I think he should have been acquitted, as he was. Because somebody tinkered with the evidence, let's be clear. There's not even a question in my mind. They salted the blood samples. Make sure he looked guilty. Yeah. But I digress. So I was an ardent OJ watcher. So let me continue. Okay. So now we're on to part B. So we have a little bit of time yet, and I can start to introduce this. This chapter deals a bit with energetics, which I think are really important, this portion of the chapter. as it were, and it dovetails in nicely. Now in lab, what we're going to do Monday is I think we're going to do the rabbit muscle lab, and if we have time, I'm going to do it out. I'm going to change the sequence a little bit, and because I want to marry what we're doing here, and whether we do the eye works then or wait for the following week to do the eye works with muscle, we'll just see how the time goes as I do that. So again, on Monday, I got to get it out of my system now. Very quiet. We're working. I could do exit stage left, running all the way. You don't have me for micro. I can't do my boo-boo. Oh, Yogi. Picnic basket. Just shut up. Nobody cares. Nobody thinks you're ever funny. So we can look at a fiber or look at a muscle. And the whole idea is tension is the force. It doesn't become motion immediately. Muscles always start by developing tension and not shortening. So we start first with isometric contraction because it's not shortening. And then once it begins to contract, generally the tension, most activities, stays the same, and we call it isotonic contraction. For those who would endeavor, it's not cosmetology class, please. For those who would endeavor, I'm still disappointed my middle one broke up with it. She was the best haircut I ever got. It was a cosmetologist. Why'd you break up with her? She never did my hair. No one ever did my hair any better. He broke up with a dental hygienist. What's going on? What?
We'll do your hair.
Thank you. Whatever's left. So I always go into where I go to like Great Clips, and I go, it could be the last one.
No.
Never can tell. But stop. It's an old joke. So we start with isometrics, we go with isotonics. And the beauty of this, for those that would endeavor to go into fields involving sport in some way, shape, or form, okay, this plays a significant role for rehabilitation. Force and duration of contraction vary. Each muscle is served by at least one motor nerve. Fine. Motor nerves, we know, hundreds of individual nerves. So the nerve, all those individual bundles we saw before, anatomically, motor nerves that are part of it, individual axons that branch of the neuromuscular junction. We refer to that unit as the motor unit, the nerve muscle functional unit, the individual branching axon to where it contacts. So the motor unit consists of the motor neuron and all the fibers, depends on the motor nerve. Okay, how many it supplies. Okay. Smaller the fiber, greater the fine control. Muscle fibers from a motor unit are spread throughout the muscle. Why? So, A, they only cause a weak contraction, but it eliminates fatigue to a certain extent. So you're not always stimulating the same area to contract. So there's a lot, very scientifically, the design is, if you will, very logical in that regard. So you can see here, so in red they have sensory, and the darker, like the blue purple, they have motor, and you can actually see the branching that's here, where they're spread out in multiple areas, at least limitedly with this. And again, we're referring specifically or not to nerves going to the spinal cord, but these are what are called lower motor neurons, the nerves that exit from the spinal cord from the ventral or anterior horn and go to the muscle. So it's an understood area, and you'll see that particularly like when they have a lot, for instance, if they have a lot of motor units, there's a lot of control versus for delicate work, for different things. How far do you move your eyes? Just a little, a lot. Those kinds of muscles, a lot of control versus a postural muscle which is basically just moving very subtly to adjust to positional change. And again, that's also part of rehabilitation in sport. So when we look, this is in the laboratory. So the first thing you have to realize is what I'm talking about now is something, and this is sort of the introduction, and we'll get the rest of it in on Monday. So when we do the eye work stuff, you get an idea what we're talking about. The simplest thing is a muscle twitch. We don't twitch. If you're someone who has a muscle twitch, it's abnormal. All of a sudden you'll see somebody and there's an irregular nerve supply or damage or inflammatory. They might all of a sudden, like you'll see they won't maybe know it. Their eyelids twitching, something like that. That's irregular. Simplest contraction resulting from a muscle fiber's response to a single action potential. Okay? We can induce the twitch in the laboratory. It's abnormal normally. And we nowadays, as you can see with the system we use, we can graphically. In the old days, you used to put that on a piece of paper with a stylus or on what was called, this is really going back, an oscilloscope, which is like an old single cathode ray tube, the old black and white TV. First monitor I got for my computer, the Amdec 310A, which was black with an orange. So there are three phases. Latency, that's the gap between excitation and contraction. Contraction, relaxation. Muscles always contract faster than they relax. So here, an isolated stimulus, sufficient to make an action potential, there's a finite amount of latency. It will contract relatively rapidly. It will relax much more slowly. And we're looking at milliseconds. So, I mean, this whole process has occurred within roughly a tenth, slightly more than a tenth of a second. A lot of variations. Eye muscles, rapid. Large muscles, your calf muscles, more slowly, hold it longer. And they show you, it's a really interesting now, and I'll leave it with this. It gives you the idea. Lateral rectus, so I was talking about an ocular muscle. We make, our eye movements are rapid. Because you're looking quickly, you hear something, you move your eyes to see something. Okay? Those are, if you remember the muscles, and I know I didn't emphasize it a lot in anatomy, you have two big calf muscles that combine into one big tendon called the Achilles tendon or tendocalcaneus. They are the gastrocnemius and the soleus. Notice how quickly the gastrocnemius is compared to the soleus. The soleus is a postural muscle. It's the one when you're standing in line waiting to get in, you're sort of like a little bit like that. It's basically contracted, subtle changes. The gastrocnemius is if you're me, my vertical leap of a half an inch. My standing broad jump of 2 inches. I have an underdeveloped gastrocnemius. That's the distinction between them. So we will look at all of this stuff going forward, and we'll start here with graded muscle responses. I want to get this in on Monday. So if we do the eye works, we're prepared for it. Thank you very much. Have a nice weekend. So much football, so little time. Who do you got?